Today I'm just going to do a brief lecture on oxidation numbers or oxidation states. And keep in mind that it's a pretty simple concept that sometimes gets made into be something a little more difficult than it needs to be. So I'm going to do the best I can to keep it simple. And hopefully this couple minutes will help you to better understand them as we're determining what compounds are going to form when elements come together. So there are some simple rules for oxidation numbers, and for the most part, the ones I want you to remember include oxidation numbers coincide with group number. Okay, group number indicates oxidation number, which is easy because remember all along we've been talking about how number of valence electrons is the charge, and charge and oxidation number are kind of the same, and so we don't want to get too different than that, but there are a few rules, and again, you can look on page 232 and you can get that list of rules. In class, I'll have also a handout for you. They'll show 10 simple rules for determining oxidation numbers. Okay? Sometimes these oxidation numbers are also called oxidation states, and so that'll be interchangeable at times. Let's do an example of an oxidation number, and we have to remember that oxidation numbers are oftentimes indicated again by the group number, but in the transition elements that can be different. Also, there is always a list of what we call common oxidation numbers, and common oxidation numbers are usually the ones we're going to see, although as you'll see in some of my examples, those common oxidation numbers are not always common, but they will be used at times. So let's start off with UF. Okay, U represents uranium fluoride. Okay, and what we're going to do is we're going to put this with the correct subscript. And the first thing you want to do is identify the oxidation numbers that you know. And in this case, we know that the common oxidation number for fluorine is always going to be a 1 minus. Okay? And since there are 6 fluorines, if you multiply fluorine oxidation state by the 6 atoms, then you'll know that the total charge for the fluorine in a uranium fluoride molecule will be minus or 6 minus. Okay? Well, since there are no subscripts for uranium, then we can go ahead and assume that uranium then must have a 6 plus charge, because remember, anytime we have a compound, oxidation states for compounds must be 0. They must be charge neutral unless it's a polyatomic ion. Okay? So in this case, if we take our 6 positive and our 6 minus, then we have that equals 0. Okay? So again, that's just one example of the use of oxidation numbers to help you. Now let's try another one. Okay? So we're going to go H2SO4, which after today you know is sulfuric acid. And again, we want to list all of the oxidation numbers that we possibly can on this one. All right. And so let's go ahead and I'm going to change pen color and let's write them in. So we know that hydrogen, its most common oxidation number is 1. and oxygen, its most common, is a -2. Okay, now we know that sulfur can have multiple oxidation states because it's in the same group as oxygen. One of those possible oxidation states is -2, but because of where it sits here as the central molecule, we have to ask, well, how can it be a -2? So let's go ahead right now and just add up the oxidation states. So we have a 2+ here, and we have an 8- here. How do I know that? Because I take these right here, this oxidation state times the number of atoms, and this oxidation state times the number of atoms. And now, knowing that H2SO4 must be electrically or charge neutral, then the only thing I can have left would be a +6. And so in this case, sulfur must have a 6 positive oxidation state if this molecule right here is going to be charge neutral. And in fact, we find out, yes, sulfur, one of sulfur's common oxidation numbers, is in fact 6+. Okay, so let's do one more just for the sake of it, and we can see how polyatomic ions work. So let's do, in this case, I'm going to just make a little squiggly here. Matter of fact, you know what? Let's extend the page a little bit, and let's do chlorate. Okay, let's do a chlorate ion. So we know we have ClO3, and it's a -1. Okay, so once again, let's go ahead and why don't you take a moment and identify the common oxidation states that you know. And you should have said that oxygen is a 2-, which is true. Chlorine is normally a 1-, but once again, we need to look at the fact that chlorine is in a position as a cation, which means that it cannot have a negative charge like it normally would because of electronegativity. So what we're going to do here is we're going to go ahead and multiply out charge times the number of atoms, and we get a 6 charge here. And we know that in this case, the chlorate ion has a -1 charge. So whatever the chlorine is going to be, it must leave us with a -1 charge. So let's take a look at this. And normally we think, well, maybe it should be 7. Well, no, it can't be 7. So let's go ahead and erase that. And what would leave us with a -1 charge? It would have to be a +5. And what we find out is that, yes, in fact, chlorine does have a +5 charge as one of its oxidation states, which means that that leaves us with our ClO3- ion. Okay, there are lots of possible practice problems on 235, and then of course at the end of the chapter. So go ahead and do some practice, and hopefully you have a pretty good idea of how to deal with oxidation states now. Okay, take care. We'll see you next time.